Hey everybody, and welcome to my video on L'Hopital's rule. L'Hopital's rule is something that's going to tie into things that you would have done earlier in a calculus class when you were talking about limits. A lot of times what calculus does with limits is they like to give you a rational expression where if you try to do direct substitution with it to evaluate the limit of the function at a certain value, you wound up getting either a 0 in the denominator or a 0 over 0 or infinity over infinity. And that is what we would refer to typically as the indeterminate form. And in order to correctly evaluate the limit of the function at that point, you had to do some kind of arithmetic. You either had to do factoring to eliminate something in the denominator that would create a 0 when you do direct substitution, or if you had radicals, you would have had to do the conjugate method to kind of rationalize the function that you would have had. Well, L'Hopital's rule is going to simplify a lot of that math, and by doing so, by taking what we know about derivatives, that's what L'Hopital's rule allows us to do. So we're going to be reevaluating how we identify the limit of a function, but we're going to be doing so with derivative techniques now, and that is how we're going to simplify some of these expressions, or to evaluate some of these expressions in order to determine what their limits are as it approaches a specific value. So essentially what we're looking at here is like what you see in the picture down at the bottom, is if you have an expression where you have some function over another function, that's typically what we think of as a rational expression of some kind. If you're going to get an indeterminate form, L'Hopital's rule states that the limit of the function as x approaches some number is going to be equal to the limit of that same function if I take the derivatives of the numerator and the denominator and then do my substitution. Here's a little bit more detailed definition of what we're doing with L'Hopital's rule. Of course, I hate this word assume, but we're going to have two functions, one in the numerator and one in the denominator, that should be differentiable over an open interval. And this right here in the middle is really what we need to be able to understand. This is the heart of what L'Hopital's rule is that the limit as x approaches a, or I think some examples are going to say as x approaches c, but you get the idea, it's just some number on the x-axis, is that if I take the derivative of the numerator and the denominator and then do my substitution to evaluate the limit of the function, they actually work out to be the same thing. And what it tells you down here at the bottom is that it's also valid for one-sided limits. So we don't necessarily have to have the ability to look at the function from both the left and right sides as we approach it, but it'll work for one-sided limits as well. Now this is it's a relatively simple task to do at this point once you have practiced several differentiation techniques. So for instance, this particular rational expression that we have, 2x squared minus 9x minus 5 over x minus 5, we're evaluating it for the limit of x minus, or as x approaches 5. And you can very clearly see that if you substitute 5 into the denominator, you're going to get a 0. In fact, you're going to get 0 in both the numerator and the denominator if you do direct substitution. Now, previously what we did when we looked at this with limits is we said, well, okay, well, you have to try factoring the numerator now to see, are you going to get an x minus 5 factor that would simplify with the x minus 5 factor in the denominator. And then you would be able to identify what the limit would be using direct substitution. And in this case, you absolutely can. You can factor the numerator, and if you do, you're going to get a 2x plus 1 factor and an x minus 5 factor. And of course, the x minus 5 factors simplify to be 1, leaving you just the expression 2x plus 1 as the limit of x approaches 5. And at that point, you could do direct substitution, giving you the limit as x approaches 5 to be 11. Well, now we're going to be showing how we can identify the same limit using L'Hopital's rule, taking the derivative of the numerator and the denominator. And this is a very simple, straightforward explanation or example to do this with. You just use the general power rule on both the numerator and the denominator. And in the numerator, you're going to get, when you take the derivative of the numerator, you get a 4x minus 9. And the derivative of the denominator is just 1. So you have 4x minus 9 over 1 as you look at the limit as x approaches 5. Well, the 1 in the denominator really doesn't matter because dividing by 1 doesn't change anything. So now we're just evaluating the limit of 4x minus 9 as x approaches 5. So it's safe now to plug in the 5 into the expression, and 20 minus 9 is going to give you the 11 that we already knew it would be when we did the factoring that we had to practice with earlier in calculus. So we get the same value either way, and that's exactly what L'Hopital's rule is allowing us to do. Now, a lot of times L'Hopital's rule is actually going to make things a lot simpler. In this particular example, the amount of work that you had to do to identify the limit using L'Hopital's rule or by factoring, I would say they're pretty similar in the amount of work that you would have to do. But in some instances, understanding what L'Hopital's rule is and recognizing you can take the derivative of both parts of the fraction and then evaluate what the limit is supposed to go to, a lot of times it's going to be simpler understanding that we have L'Hopital's rule that we can use. So here, now we have an expression, and this is something that we would have had to use the conjugates with in the numerator. We would have had to multiply both the top and bottom of the fraction by the conjugate of the square root of 4 minus x minus 3, and then tried to simplify it so where, again, we wouldn't have that x plus 5 problem in the denominator, because clearly you can see if you just do direct substitution, you're going to get a 0 in the denominator. Now this one has a little bit of catch to it, and it really has to do with the fact that there is a negative sign inside of the radical. Because of that negative sign inside of the radical, we're going to have to look at using the chain rule. And I know this keeps popping up. It just keeps rearing its ugly head. It started doing it in Unit 2 when we had to use a chain rule, where the chain rule basically says if I have some composite function, f of g of x, then its derivative would be the derivative of the whole thing times the derivative of the inside part. So when I start using L'Hopital's rule for the numerator, we're going to have to use the chain rule on that expression. And it's only because of the negative sign on the x value. So let's see how it's going to look. I'm converting it from a radical form into an exponent. And now when I take the derivative, this is what I'm going to wind up getting. Now let me be clear about what I'm doing from step 1 to step 2, looking at this expression here. So if I say 4 minus x to the 1/2 power, I'm going to take the derivative of the whole thing. So using the general power rule, we're going to multiply the 1/2 to the, whatever the coefficient was. In this case, it's 1. And inside the parentheses, they stay the same. We have, 4 minus x. And we drop the exponent value by 1. So 1/2 minus 1 gives me a negative 1/2 exponent value. But now we have to multiply it by the derivative of the inside part. Well, the derivative of the inside part is this bit right here, the negative x. So the derivative of negative x is a negative 1. So we wind up with negative 1/2 times 4 minus x to the negative 1/2 power, and then we move that negative exponent to the denominator, giving me the negative 1 over 2 times 4 minus x to the 1/2 power, or if you want to write it as 2 times the square root of 4 minus x, that would be fine also. But by doing the derivative of the numerator and the derivative of the denominator just gives you a 1. And because we have a 1 now, it looks like it's going to be relatively safe to go ahead and do my direct substitution. So plug in the -5 in for the x value, and here you can see I'm doing the square root because just in my head mentally I understand that the number 4 minus -5 is going to give me a 9, but my mind processes the square root of 9 a lot easier, a lot better than 9 to the 1/2 power for some reason. So that's why I'm converting it back into a radical form at this point. If you want to leave it as an exponent, you understand 9 to the 1/2 power is just the square root of 9, great. That's fine. So we get -1 over 2 times the square root of 9, which is going to be a 3. So we wind up with a value of -1/6. Now, finding the derivatives of some of these things can be, some of them are going to be more tricky than others, but considering the amount of differentiation techniques that we have at our disposal, it still makes sense to try to use L'Hopital's rule to find the limit of a function when you know doing direct substitution is going to give you some indeterminate form, something over 0, infinity over infinity, something like that. Now, the nice thing about L'Hopital's rule is that you can actually use it multiple times. So if you take the derivative of a numerator and the denominator, and direct substitution still results in an indeterminate form, you can continue taking the derivatives. You can go to the second derivative or the third derivative, however many times you need to, in order to prevent that indeterminate form. Now on this one here, if you notice what we're seeing, and I want to kind of write this out here for you also. Let's take a look at just this, just this denominator here, e to the -x power. Now you understand that e to the x power, the derivative of e to the x is e to the x. But because of the negative sign on e to the x power, again, we're going to use the chain rule. So the derivative of the whole thing would just be e to the -x. But the derivative of the inside part in this case is going to be the derivative of that exponent there. So the derivative of -x is a -1, giving me negative e to the -x power. And that's why we're seeing that expression here in the denominator. Now, don't worry too much about the chain rule. I understand that we are seeing it kind of popping up here and there, and we've talked about it several times in different lessons, but it's not going to be something really prevalent in things that you're going to be seeing. I think it's just unfortunate some of the examples that got chosen for us to use here. But anyway, now what we're going to be doing is we just kind of continue on, because at this point, if I do substitution again, I'm going to wind up with another indeterminate form. So I can continue somewhere, there it is, I can continue taking the derivative of both the numerator and the denominator. So in the denominator, if you notice here, the negative sign has disappeared. That's because if I take the derivative of negative e to the -x power, well, the derivative of this expression is itself negative e to the -x power. But again, using the chain rule, I have to take the derivative of this part here, which would be a -1, and the negative times the negative gives me a positive e to the -x power. So that's how I'm getting the derivative of e to the -x power in the denominator. And now, and this is really because the x value, if you notice, is no longer in the numerator. This is really where we can do our substitution, where I'm going to say, moving the e to the -x, I'm moving it to the numerator using properties of exponents, and now we can do our substitution. Well, e to the negative infinity, that's just going to go to 0. So 2 times 0 is 0. Now here, this is a really nice example. This is a third-degree polynomial over a third-degree polynomial, and trust me, you can certainly do the substitution, plug in the -2, and verify it for yourself, but this one will give you 0 in the denominator if you do direct substitution. So if I take the derivative of the numerator and the denominator, we wind up with this expression here. Now this is where you should check it first. You know, do I need to keep going at this point? And if you plug in the -2 into the expression that we have now, you're still going to wind up with 0 over 0. Well, this is what L'Hopital's rule allows us to do. We can keep taking the derivatives. So now let's take the second derivative of the expression that we have, and we wind up with 6x plus 2 over 6x plus 16. Now we can check and say, okay, well, if I plug in the -2, am I going to get 0 over 0? And in this case, it should be pretty obvious that we're not. We're going to get a -12 in both the numerator and the denominator, but the 2 and the 16 that are there, neither of them are going to create a 0 if we do our direct substitution. So that's what we're doing. And really, at this point here, this limit should be gone because once we actually evaluate it, we don't write the limit anymore. But you know, nobody's perfect, I guess. And now we can look at the limit, and we wind up with a final expression for the limit of this expression as x approaches -2 to be -5 over 2 or -2.5, however you wanted to write it. Now, this one here, I think is a little bit interesting in the example that it was chosen to use, because you don't actually have to use L'Hopital's rule on this one. Now, did I do L'Hopital's rule? Yes, but I'm also going to explain why you don't have to. So the first thing I want to do is I want to recognize I can break this up into two separate fractions where I'm showing that the limit of sine over x times the limit of 1 minus cosine of x over x, those are equivalent expressions. Now, here what we're going to do is we're going to, okay, so let's take the derivative of both parts, just like what L'Hopital's rule says to do. Okay, we can. But this is a really good example of trying not to have the blinders on and just thinking that I only have this one approach to working out the problem. And some of you watching this may be able to predict exactly what I'm going to say as far as an alternate method that you could work with. But once I have the individual fractions, essentially I've kind of factored the denominator, and you know, you can see if we multiply everything back together, we're going to wind up back where we started. And here, there it is. The derivative of both the numerators and the denominators, in this case, will give me cosine of x over 1 times the limit of 0 of sine of x over 1. So the ones in the denominators, again, don't really matter. So I can do my substitution at this point and say cosine of 0 times sine of 0. Well, cosine of 0 is 1 and sine of 0 is 0, so the whole limit goes to 0. Now, let me explain why I'm saying you don't truly need to use L'Hopital's rule to understand it or to find the limit here, and this is really the row that we would want to take a look at. Some of you hopefully are going to recognize that when we were studying limits, there were two special trig limits, and those are exactly what we're seeing here. This limit as x approaches 0, sine of x over x, that's always going to simplify to be 1, and this one here simplifies to be a 0. So, what we would do is I could just say, well, this expression simplifies to be a 1, this expression simplifies to be a 0, 1 times 0 is 0. But L'Hopital's rule still gives us a valid result, so it is what it is. Now, here, we're getting close to the end. I think there's only a couple more examples, but what I would really like you to do, this is a very good example to practice with. I would like you to pause the video at this point and try to identify what is the limit of this particular function as x approaches 1 using L'Hopital's rule. And the reason why I'm asking you is because it's asking you to use L'Hopital's rule, and the differentiation techniques are going to be something that's besides just the straight power rule. So pause the video, try to find the limit of this, and when you're done, hit play and see how I did it. So presuming that you've done what I've asked you to do, here we're going to begin taking the limit of both sides, or both the top and the bottom of the denominator, or I'll get it right eventually, both the numerator and the denominator of the fraction. There we go. So the natural log of x is just 1 over x. The derivative of negative x is negative 1, and the derivative of 1 is 0, so we don't bother writing it. Same thing with the minus e in the denominator. Remember, e is just a number. It's about 2.718. So the derivative of e is still the same thing as like saying the derivative of 1. The derivative of a constant is 0. So we wind up with e to the x power here. Now, you may want to, at this point, consider rationalizing depending on what you have for the functions or for the fractions that you see. But in this case, we can go ahead and just do some direct substitution. So plugging in the 1, we're not going to get any kind of oddity here. And in the numerator, we're going to get 1 minus 1, which will be 0 over e to the first power, which is just e. And of course, 0 divided by anything is just 0. So the limit here is 0. And again, this would be another really good example. This is going to be an example where you'd have a repeated use of L'Hopital's rule. So again, I encourage you, I very much would like you to pause the video and attempt to identify the limit of this particular function using L'Hopital's rule and the power rule for differentiation and see what you wind up getting. All right, so hopefully you've paused the video, worked out what I told you to do. So here we start off with finding the first derivative of the numerator and the denominator, and this is what we end up with. Now the problem is because we're approaching infinity, in this case I'm going to wind up with an infinity over an infinity when we compare essentially the numerator and the denominator's leading terms. So I'm going to find the second derivative now, which would give me 18x plus 10 over 24x, which again, the leading terms, 18x over 24x, as they approach infinity, the plus 10 in the numerator really doesn't matter, and that's still going to give me something infinity over infinity. So I keep going. Now I'm on the third derivative, which would be just 18 over 24. Now, can I find the limit of the function if I don't have a variable to substitute into? And the answer is absolutely you can. So here, because even though that the x values are no longer present in that ratio of 18 to 24, that doesn't mean that the limit doesn't exist. We just take the limit of whatever that fraction is, which is in this case 3/4. So the limit of that third degree polynomial expression divided by a third degree polynomial expression, the whole limit simplifies to just be 3/4. And I believe this is our last example, and again, this is a relatively good one to try to practice with. The one thing that I'm going to encourage you to try and think about before you try working it on your own is taking a look at this guy right here, because again, we're going to be taking a look at using the chain rule on that guy right there. So the chain rule for e to the 2x power, if I try to take the derivative of that, that's going to give me e to the 2x power by itself, but I have to also take the derivative of the inside part. So the derivative of the inside part would be a 2. So I would write the derivative of e to the 2x power as 2 times e to the 2x power. So keeping that in mind, please go ahead and try working out the limit of this expression, understanding how I'm, kind of using the chain rule on the e to the 2x part, and see what you get. When you're done, hit play and compare your work with mine. So ideally, you have, attempted to work out the problem here, find the limit of the expression. And so here, when I take the first derivative, this is what I wind up with. Now, if I do direct substitution at this point, again, just kind of looking at the leading terms of the 8x and the 2 times e to the 2x power, if I do direct substitution there, I'm still going to wind up with an infinity over infinity. So we have to find the second derivative of the numerator and the denominator. Now, again, you still have to use the chain rule on the 2 times e to the 2x power in the denominator, and there it is. And we wind up now with 8 over 4 times e to the 2x power minus 1 over x squared. Now at this point, even though we're going to have an x value in the denominators that we're going to be approaching infinity with, we're not going to have an x value in the numerator that's going to give us infinity over infinity. So we can do our substitution at this point, and the expression in the denominator, 4 times x to the 2 times infinity power minus 1 over x to infinity, well, the first expression on the left simplifies to just be infinity because you're raising something to infinity, so it becomes infinity. And 1 divided by infinity, 1 divided by an exceptionally large number, goes to 0. And so we wind up with 8 over infinity, essentially. And again, 8 divided by an exceptionally large number is still going to go to 0. So that's why the limit in this case works out to be 0. So that, I believe, is the last example. Yeah, there it is. And so L'Hopital's rule, again, allows you to use differentiation techniques that we've been studying to find limits of functions that would otherwise either be giving us simply an indeterminate form, which would require us to use some other kind of arithmetic technique, such as multiplying by conjugates, factoring, things of that nature, maybe rationalizing some fractions. And by using those differentiation techniques, we are able to evaluate the limit of functions that would normally give us an indeterminate value relatively quickly. Now, of course, some instances, like the very first example, the amount of work using L'Hopital's rule versus factoring it and simplifying it, really not much of a difference. But for some of the other problems, as hopefully you've identified that, yeah, it still looks a little funky trying to take the derivative of some of these things, but after having almost 2 units worth of practice with differentiation techniques, hopefully they're not that challenging to use at this point. But anyway, thank you very much for watching the video. I hope you guys are all doing well. If you have any questions, you know how to get in touch with me. And until next time, guys, thanks for watching. Take care and be safe.